All right, I'm sorry for the delay. Let's begin. So November 2020, paper 4.1 and paper 4.3, these are the two papers that we're discussing today. We will only be doing the difficult questions from these two papers. Let me know the questions that you find difficult, that you found difficult from these two papers in the poll that's posted in the WhatsApp group. And we will be looking at all of those questions in this class. All right. Just a reminder that you look at the polls posted in the WhatsApp group and let me know the questions that you find difficult from both the papers. So right now from 4.1, I just see two questions that you guys are asking about. And they are questions 5 and 7. Let's start with these questions. Question number 5 and question number 7. November 2020, paper 4, variant 1. Okay, so this is the first question that you're asking about. It says two particles of masses 0.8 kg and 0.2 kg. They're connected by a light and extensible string that passes over a fixed smooth pulley. The system is released from rest, so it starts from rest. These are the masses. Both particles are 0.5 meters above a horizontal floor. You can see that in the diagram as well. And in the subsequent motion, 0.2 kilograms particle does not reach the pulley. So they're basically saying when the 0.2 kilogram particle goes upwards, it does not reach the pulley. So we don't have to worry about this particle colliding with the pulley. Okay. Now, the first part says, show that the magnitude of the acceleration of the particle is 6 meters per second square and find the tension in the string. Now, this is a standard Newton's second law of motion problem. You can see you've got two particles hanging like this. What are the weights? What are the forces acting on those two particles? On the first one, on the one on the left side, you've got downward force acting. That's the weight of the particle. That's 8 Newton. Upwards, you would have tension of the tension in the string. Similarly, on the right side, you've got weight acting in the downward direction. That's 2 Newton. And there will be tension acting in the upwards direction. Okay, these are the forces acting. And that's it. There's nothing else here. What do? We just use Newton's second law of motion on each of these objects one by one and find the tension and acceleration. Let's use it on the particle on the left side first. In which direction is that particle moving? The particle that has more weight, that will be moving downwards, and the particle that has less weight, that will be moving upwards. So 8 Newton particle will be moving downwards. So what's the forward force for that? That's 8. Backward force is T equals mass, which is 0.8 into acceleration. That's one equation that we get. And now similarly on the other particle, we can say forward force, since it's moving in the upward direction, forward force is T, backward force is 2. That equals mass, which is 0.2 times acceleration. You can find the value of T and A from this. From the first equation, T turns out to be 8 minus 0.8 times A. From the second equation, T turns out to be 2 plus 0.2 times A. Now you equate both of them. That gives you 8 minus 0.8 times A equals 2 plus 0.2 times A. 0.8A comes to the right side, and that gives you A equal to 8 minus 2, which is 6. And that's one thing that we were looking for, acceleration value. That turns out to be 6 meters per second square. Now put this back in any one of those equations to find the corresponding value for tension. And that will be T equals 8 minus 0.8 into 6, which is 16 over 5 or 3.2 Newton. We've got the acceleration and the tension. That's what we were looking for in the first part. Okay, pretty straightforward. Now let's look at the second part. It says, when the 0.8 kg particle reaches the floor, it comes to rest. Find the greatest height of the 0.2 kg particle above the floor. Okay, so now what happens is, so we're done with the forces. I can just get rid of the forces from here now. When the particles move this 0.8 kg particle reaches ground at some point, and then it stays there at rest. Now, in the meantime, the other particle would have also moved upwards, and it would have come to some point around here. Okay, the same distance that the first particle moved downwards. Now we're talking about the 0.2 kg particle, right? How much distance does that travel? What's the greatest height that particle reaches? Now think about it. It starts from rest, so its initial velocity here was 0 meters per second. How much distance does it move upwards until this point when the first particle reaches the ground? The distance above the ground was 0.5 meters. So the particle on the right side would have also traveled 0.5 meters until that point when the first particle hits the ground. But then when it reaches this point, it would have some velocity, some positive velocity, because it was moving upwards. Because of that velocity, it will keep moving upwards for a while, even though at this point, string will become slack, remember, because when the other particle hits the ground, now it's this position. This is how the string looks like. Now, as soon as this particle on the right side moves slightly upwards, there's going to be slack in the string. The string will be slack, and there will be no tension anymore. And this particle will actually be moving under free fall after that. So what we can do is we can actually divide our journey for this 0.2 kg particle into two parts. And I generally recommend that you mark these points here on the diagram like this. You say this point is X, where the particle started, and then this point is Y, when the 0.8 kg particle hit the ground. From X to Y, the string is slack. And then at Y, from X to Y, the string is taut. At Y, the string now becomes slack. The particle moves upwards for a little more until it reaches its greatest height. Let's say this point is Z. And then it will start going down after that. From Y to Z, the string is slack, because at Y, the first particle, the 0.8 kg particle, had hit the ground. So when the 0.8 kg particle hits the ground, after that, the string would be slack. Okay. And now we consider both of these two parts of the journey separately. Now, let me explain what I mean by that. You've got the first part, XY. We've got the second part of the journey, that's Y to Z. Both of them are in the upwards direction, so we can take upwards positive for both of them. What do we know about X to Y? From X to Y, we know that the displacement is 0.5 meters. That's what we know about X to Y. What else do we know from X to Y? We have found the acceleration while the string was taut. Remember, X to Y is the part when the string is taut. Y to Z is the part when the string is slack. While the string was taut, we know that the acceleration was 6. So we know the acceleration for this part of the journey as well. That was 6 meters per second square. We also know the initial velocity because the particles started from rest. So the initial velocity was 0. This is the information that we've got about the first part of the journey. What about the second part of the journey? From Y to Z. We know the final velocity because at Z, when it reaches its greatest height, the final velocity would be 0 at that point. So we can say we know that V equals 0. What else? The particle is in free fall now. What about acceleration? We are taking upwards positive. Acceleration acts, gravity acts downwards. The acceleration value will be negative 10. That's the second piece of information that we've got. And what we need to find out is displacement. Now, this is not enough information. We need one more thing to be able to find displacement. What we can do is we can say Y is common between these two parts of the journey. Using the first part of the journey, what we can do is we can find the velocity at this particular point, velocity at the point Y, and see what that turns out to be. How do you do that? You can use this equation, 2as. So remember what we're looking for? We're looking for V. Why? Because that can be used as the initial velocity for the second part of the journey then. 2as equals V squared minus U squared. Let's see what we get from this. 2 into 6 into 0.5 equals v squared minus 0 squared. And that gives you under root of 6. This is the velocity at the point y. If this is the velocity at the point y is the initial point here. So the initial velocity here would be square root of 6. All right. And now what we can do is we can find the displacement for the second part of the journey and see what that turns out to be. Let's find that. For the second part of the journey, again, we can use the same equation here as well. 2as equals v squared minus u squared. What would that be? 2 into minus 10 into s equals 0 squared minus under root 6 whole squared. What do we get from this? 6 divided by 20, and that's 0.3. Displacement here turns out to be 0.3. That means from y to z, the length is 0.3. Okay, so now we know that this distance is 0.3, then this distance is 0.5, and then it was already 0.5 above the ground. So what's the greatest height then? We just add all of these numbers up. Greatest height reached by that particle, that will be 0.5 plus 0.5 plus 0.3, and that is 1.3 meters. Okay, and that is what we were looking for here. The greatest height of this particle is 1.3 meters. Make sense? Yes, Abdullah?
सर सर मुझे प्रॉब्लम आई थी क्वेश्चन नंबर 4 में. मैंने आपसे एक चीज क्लियर करनी थी. सर क्वेश्चन नंबर 4 में हमें अब डिस्टेंस हमें चाहिए, तो एक्सेलरेशन को हम दो दफा हम इंटीग्रेट करेंगे. तो उससे लेट्स सबसे पहले एक्सेलरेशन को हमने वेलोसिटी हमारे पास आ गई इंटीग्रेट करने से, तो एक उससे कांस्टेंट आया प्लस सी. तो जब हम वेलोसिटी को दोबारा इंटीग्रेट करेंगे टू मेक डिस्टेंस इक्वेशन, तो हम दोबारा एक और कांस्टेंट नहीं आएगा, एंड जो पहले जो प्लस सी आया था उसको हम इंटीग्रेट करेंगे.
जी बिल्कुल, एक और कांस्टेंट आएगा.
बट मार्किंग स्कीम में सिर्फ एक था प्लस सी.
लिमिट्स यूज की होंगी ना उसमें. Okay, so the question is, when we integrate, so we have acceleration given. So that is talking about question number 4. We have acceleration given. And what we need to do is we need to find the distance the particle moves before it comes to instantaneous rest. Now, when we go from acceleration to displacement, we have to integrate twice. So we have acceleration equal to 60 minus 18. When we integrate it, we get 6t squared over 2 minus 18t plus c, and we get one constant here. And then when we integrate this once more, we would get another constant after that. So are we going to have two constants? Yes, if you do it like this, you would have two constants. However, what you can do instead is, you can use limits in this case instead. So what are we looking for? First of all, it says it starts from rest. So that means we can use that information to find the value of this c first. Because since it starts from rest, that means when time equals 0, the velocity value will be 0. And that will give us the value of c. In this case, you will see the value of c will turn out to be 0, because if this is 0 and these are all zeros as well, the velocity function therefore turns out to be v equals 3t squared minus 18t. Now that earlier c is finished because we know that the value of c is 0. Right? You figure that out first. And now that we have this value of this function v, now we need to find the distance traveled by the particle before it comes to instantaneous rest. Now, first of all, you need to find what that point is when it comes to instantaneous rest. For that, what you do is you've got the velocity function that's 3t squared minus 18t. Let's put v equal to 0 in this first, and let's find the point when the particle comes to instantaneous rest. And that gives us 0 equals 3t squared minus 18t. Take 3t common, that leaves us with t minus 6 inside. We get t equals 0 and t equals 6. So the particle started from rest and then it came to instantaneous rest again when t was equal to 6. Now we have to find the displacement or the distance traveled by the particle from t equals 0 to t equals 6. Now for that, what we can do is we can just integrate this velocity function again to find the corresponding displacement function. And that's going to become 3t cubed divided by 3 minus 18t squared divided by 2. But since we're looking for displacement from one point to another, we can directly do this by using limits. So they would have used limits there. That's why probably they ignored the c here. You can use limits from 0 to 6, right? Because that's what you are looking for. Distance traveled from 0 to 6, and there's no change in direction. So you can just use this formula directly. And that gives you 6 cubed minus 9 into 6 squared. Subtract from this the case when you input t equal to 0, that will just be 0. And that gives you 216 minus 36 into 9. That's negative. Velocity function was this. At time 0, at time 1, it is negative. And its initial acceleration was also negative. Yeah, so basically it was moving in the negative direction, and that's okay. Because it was moving in the negative direction, its displacement is turning out to be minus 108. They asked you for distance p moved. So when you talk about distance, you will make that positive. You'll say the distance moved is going to be 108. It's turning out to be negative. The displacement is turning out to be negative because it's moving in the negative direction. You can see when time is equal to 0, or time is equal to 1, for instance, velocity is negative. Velocity is minus 15. That means it's moving in the negative direction. That's why this displacement is negative. But that's what you get at the end, 108. So that's what they would have done. They would have used limits. Even if you did not use limits, you can also do it directly. In this case, you would say t cubed minus 9t squared. You would have another c here. But then what's the value of this c? You also know that when time equals 0, in this case, displacement is also 0. So that will also give you this c equal to 0. So both of those c's turn out to be 0 in any case. So that's why they would have probably just ignored it in one of them if they did it like this. Is that okay?
Yes, sir.
All right. Okay, so that was question number 4. We actually just ended up doing that as well. But now let's move on to the next one that you asked about. This was question number 7. Okay. So the next question from this paper is question number 7, and that's it for this paper. Please have a look at the other paper as well if you haven't already looked at that. Let me know the questions that you found difficult so we could discuss some of those questions as well. Okay, question number 7 from this paper. That's the next one that you want to look at. It says 3 points A, B, and C, they lie on a line of greater slope of a plane inclined at 30 degrees to the horizontal with AB equal to 1 meters and BC is also equal to 1 meters as shown in the diagram. A particle of mass 0.2 kg is released from rest at A and slides down the plane. The part of the plane from A to B is smooth, so this part is smooth. The particle was released from rest. Mass is 0.2 kilograms. AB part is smooth. The part of the plane from B to C is rough with coefficient of friction mu between the plane and the particle. Given that mu equals this, find the speed of the particle at the point C. Okay. So how do we think about this? A to B part is smooth and then B to C part is rough. Okay. I think we can do it both ways. We can do it using the acceleration formulas and also using work energy. So you can do it either way. Let's do it using forces and acceleration and see what we get from that. So we have 2 parts of the journey. One part from A to B and another part from B to C. Let's see what's happening from A to B and what information do we have about the part A to B. And then we'll think about the part from B to C. A to B part is smooth, remember. It's a smooth inclined surface. And the only force acting on the particle is the weight of the particle, or a component of weight. That's the only force acting. There's no other force acting on the particle apart from weight. When that is the case, remember what acceleration is given by? When weight is the only force acting on a particle on an inclined surface and it's a smooth surface, acceleration is given by 10 sine theta, where theta is the angle of inclination of the plane. That's the value of acceleration. The particle is moving down the plane. This is also acting down the plane. If we take this direction as positive, acceleration is going to be 10 sine theta. Okay? So acceleration value is going to be 10 sine theta. In this case, that's 10 sine 30. And that turns out to be 5 meters per second. That is something that you should remember. Whenever you have a smooth inclined surface, whenever you have a smooth inclined surface with weight as the only force acting, acceleration is given by 10 sine theta. Okay? You can use that directly. Otherwise, you'll have to use Newton's second law of motion to find acceleration. You don't have to do that. You can just write this value directly. So this is 10 sine 30. Now, what else do we know from A to B? We know initial velocity, it started from rest. We know displacement from A to B is 1 meters. That's all the information that we've got from A to B. What we do not know is the time taken, and we also do not know the speed. Now, finding the final speed, the speed at B would be helpful, because then we can use that as initial speed for B to C part of the journey. So let's find the final velocity using this information from A to B. Let's see what V turns out to be. Which equation do we use for that? We've got V, A, S, and U. We can again use that equation that we used in the last question as well. 2AS equals V squared minus U squared. Let's see what we get from this. 2 into 5 into 1 equals V squared minus 0 squared. And V turns out to be square root of 10. That's the velocity of the particle at the point B. Now that will become the initial velocity for B. Now for B to C part, okay? This is the velocity at the point B. Now, what do we know about B to C? From B to C, the only information that we've got is the displacement as of now. And then we have also found the initial velocity, that will be this, but there's nothing else that's given. However, we are given that this part of the surface is rough now. Can we find acceleration in this part of on this part of the surface now? Let's think about it. Let's say the particle is here. What are the forces acting on this particle? You can use that to find acceleration, right? What's the weight of the particle? Weight acts vertically downwards. That's given to be, mass is 0.2 kilograms, so weight is going to be 2 Newton. That acts vertically downwards. What other force is acting? We've got reaction that acts in this direction. Since the particle is moving downwards, friction is going to oppose that. Friction will act in this direction. And that's it. All right, these are the forces that are acting. Now let's resolve this 2 Newton. There's one component that's going to be here. If this angle is 30 degrees, this is also going to be 30 degrees. So this component turns out to be 2 cos 30, and the other component that's acting parallel to the surface, that will be 2 sin 30. Now these two components are going to be equal. They're always equal, perpendicular to the surface, because the particle is not moving perpendicular to the surface. It's only moving along the surface. So we can say R equals, in B to C part, R equals 2 cos theta, 2 cos 30. Along the surface, we can use Newton's second law of motion. Forward force minus the backward force equals mass into acceleration in this direction. The particle is moving down the plane. What's the forward force? The forward force is going to be 2 sin 30. This is the forward force. What's the backward force? Backward force is friction. 2 sin 30 minus F, that equals mass, which is 0.2 times acceleration. Sin 30 is 1 over 2. So 2 into sin 30, that gives you 1 minus friction. Since the particle is moving, friction is at its maximum value, which is mu times R. So it becomes 1 minus mu R equals 0.2 times A. And you can input the value of mu and R here. mu is 1/2 into √3. That's what they've given. 1/2 into √3. That's the value given here. What about R? You can put this on your calculator. 2 into cos of 30. That's giving me, what's cos 30? Cos 30 is √3/2, right? Why am I not getting an exact answer? Okay, yeah, my calculator is in radian mode. Let me change that. 2 cos 30. That's √3. So R is turning out to be √3. Let's put that here as well. R is √3. That equals 0.2 times acceleration. Now from this we get 1 minus 3/2 equals 0.2 times A. You can find the value of acceleration from this and see what that turns out to be. 1 minus 3 divided by 2 divided by 0.2. Let me do that again. 1 minus 3/2, then divided by 0.2. That's minus 5/2. I'm getting acceleration to be minus 2.5 meters per second square. That's the acceleration that we're getting for this part of the journey from B to C. Now, what else do we know about this part of the journey? We know the initial velocity that's coming from here because the velocity at B was √10. That will be initial velocity for this part of the journey. U equals √10. We know acceleration now. Acceleration is equal to minus 2.5. And we know the displacement, that is 1. You can see this part was also 1 meter. We need to find the final velocity at the point C. Which equation do we use for that? We'll again use the same equation. 2as equals v² minus u². These are the same 4 quantities that we were using earlier. 2as equals v² minus u². It's just input values. 2 into minus 2.5 into s, and that gives you 1. That equals v² minus √10 whole squared, and that gives you the final velocity. That's not too much work for 8 marks. That's all that you've got to do. What do we get from this? 2.5 into 2 divided by 10. No, sorry, plus 10. Minus 2.5 into 2 plus 10. That is 5. v² turns out to be 5. And then v turns out to be √5. That should be the velocity or the speed of the particle at the point C. That's what we were looking for. Is that okay? That's 8 marks, not that much work. This is all that we had to do here. Any problems with this? Yeah, you could use the energy method as well. That should also work. Yeah, but this was also not that difficult. This was also pretty straightforward. 8 for 8 marks, that's very little working. Okay, let's move on. Given instead that the particle comes to rest at C, find the exact value of mu. Okay, now what does that mean? In the first part, inside the part, we were given that mu equals this. Now that is no longer relevant. They're saying given instead. That means this is not the value of mu that you can use anymore. Nothing changes from A to B. A to B, everything remains exactly the same. This part remains unchanged. The only thing that's changing now is B to C part, the rough part of the surface. Okay. And what is changing? We don't know what the value of mu now is. We can use all of the same working again. Almost the same working. Let's see what we can use here. So this is what we knew about B to C part. Okay. Now what is changing? we are not given the value of mu anymore. So we can't use mu equal to under root 3 over 2 here. R remains the same as before. Instead of this, we are going to write mu here. Okay. This is the equation that we get. We can use this somehow to find mu, but we can only find mu if we know acceleration. We are given some other piece of information now in this part. What we can now do is we can say the initial velocity was under root 10. Displacement was 1. These were two things that we knew about B to C part of the journey. Right? Now they've also given that the particle comes to rest at C. So at the end point, the velocity of the particle becomes 0. So we know the final velocity is 0. And now, since we want to find the value of mu, what we can do is we can find acceleration using this information. We can input that value of acceleration here, and that will give us the value of mu. So it's the same work, just done in the other way around. 2as equals v square minus u square. These are the same equation that we use here as well. 2 into a into s, which is 1, equals v squared, which is 0 squared minus u squared, which is under root 10 whole squared. What does that give us? 2a equals minus 10 and a equals minus 5. So now we know that the value of acceleration is negative 5. We put that here. We say let's input a equals minus 5. And that gives us 1 minus under root 3 times mu. That equals 0.2 into minus 5. 1 minus under root 3 mu equals minus 1. Minus under root 3 mu equals minus 2. And the value of mu turns out to be 2 over under root 3. You can write that in decimals and see what that is. Do you want an exact answer? Oh, I'm sorry, they want an exact answer. So that's your final answer, 2 over under root 3. You just leave it like this. And that's what you were looking for. Make sense? No problems? That was the last part of this question, and that ends this paper. Please have a look at the other paper quickly. Let me know the questions that you want to discuss from that other paper as well. If there are no problems here, let me move on to the next one. November 2020, paper 4, variant 3. This is the next paper. Again, let me know in that poll which questions you found difficult from this paper. Okay, let's start with this one. November 2020. Let me just skim through some of these questions as well, because I don't see many votes in that poll yet. Just have a look at these questions while I scroll. Okay, so there's only one person who's asked about this. I'll just explain that to you quickly. Since they're asking for two possible values, and in the question they say, A starts moving at 1.5 meters per second after collision, and B starts moving with this speed, 3 meters per second. They've given speed, but not direction. So what's happening is, let's say A is coming from here and B is here. B was at rest earlier. And A was moving towards B with speed 6 meters per second. After collision, we are given their speeds. One is 1.5 and the other is 3 meters per second. But they have not mentioned in which direction. Now, since B is being hit from the left side, B can only move in one direction. B will only move in the right direction. There's no other possibility for B. However, A is hitting B from the left side. Now, there are two possibilities for A. A could either go to the right side. It could keep moving to the right side. That would be one possibility. And the other possibility would be that you say A actually moves to the left side with the speed 1.5 meters per second. This will be one case. This will be another case. You'll find the loss in kinetic energy for both of those cases separately. And that will give you these two possible values that you're looking for. Okay. So basically, each of these cases will give you a different value of M here, and then you'll get different possible values of loss in kinetic energy from that. So this is where the two cases are going to come from. In one case, you take that A is moving to the right after collision, and in the second case, you take that A is moving to the left after collision. And then you can find the loss in kinetic energy from each of those two cases separately. Okay, I hope you can do that now. Try this. You make those two cases, and then try it. Okay, we have 5, 6, 7, 5 alphas, not many votes. Let me quickly have a look at this. We have 6 and 7. Okay, let's do these three questions quickly. Questions 5, 6, and 7 from this paper. Let's start with this one. It says a particle P moves in a straight line. It starts at a point O. So this is November 2020, paper 4, variant 3. That's what we're doing. And we will be doing questions 5, 6, and 7 from this paper. All right. Okay, let's start with this. A particle P moves in a straight line. It starts at a point O on the line at time t seconds after leaving O. It has velocity v meters per second, where v equals this. Find the values of t for which p is at instantaneous rest. Rest means velocity is 0. You put velocity equal to 0 there, and that gives you 0 equals 4t squared minus 20t plus 21. Solve this quadratic equation and you'll get the result. Now, you can't write down the answers directly. You have to show working. You can either use quadratic formula or see if factorization is possible. In this case, you have 84, 16, and 4 are not going to work. 14 and 6. Yeah, 14 and 6. So we can do factorization here. 4t squared minus 14t minus 60 plus 21. We get two factors from that. 2t minus 3 and 2t minus 7. Right? You get two possible values of t from that. T equals 3 over 2 or t equals 7 over 2. That's what we were looking for. These are two possible values of t where when the particle is at instantaneous rest. Now it says find the initial acceleration of p. Initial means when time equals 0. Find the acceleration when t equals 0. All right, we've got the velocity function. How do you go from velocity to acceleration? You have to differentiate it. So it becomes 4t squared minus 20t plus 21. That's the velocity function. How do you find acceleration? Is differentiated. That gives us 8t minus 20. Now you put t equal to 0 in this. And that gives you acceleration equal to 8 into 0 minus 20, which is minus 20. That is the initial acceleration of this particle P. Okay. That turns out to be negative 20. Let's move on to the next one. Now it says find the minimum velocity of P. Minimum velocity, what does that mean? Velocity is a quadratic function. It's going to look like this. We're looking for the turning point. How do you find turning point of a function? Find the derivative for that equal to 0. This is the velocity function. 4t squared minus 20t plus 21. Let's differentiate it. We've done that already. Acceleration is the derivative of velocity. You can just put acceleration equal to 0, or you can think of it in terms of functions. You can say dv over dt, derivative of v with respect to t, that's 8t minus 20. When we're looking for minimum velocity at that point, derivative should be equal to 0. We get 8t minus 20. The value of t turns out to be 20 over 8, which is 2.5. Put this value of t back in the function, back in the velocity function, you get the corresponding minimum velocity. V equals 4 into 2.5 squared minus 20 into 2.5 plus 21, and that should give you the result. 4 into 2.5 squared minus 20 into 2.5 plus 21, and that's giving me negative 4 meters per second. That's the minimum velocity of P. All right, again, pretty straightforward. This is what we had to do here. Okay, let's move on to the next one. Now it says, find the distance traveled by P during the time when its velocity is negative. Now, when is velocity negative? Now, let's think about this. We know the velocity is 0 at time 3/2 and at time 7/2. And it's a U-shaped graph because it's a quadratic function. Velocity is a quadratic function here. This is what the graph looks like for that velocity function. And what we have done is t equals 3/2 and 7/2. We know the points where the graph crosses the x-axis. This is 3/2. This is t-axis, right? Time axis. And this is 7/2. Where is velocity negative? Velocity is negative in this part. We need to find the distance traveled in this part of the journey. From time equals 3/2 to time equals 7/2. Now, there's no change in direction in this part, right? Direction is changing at 3/2 and 7/2. So initially, from 0 to 3/2, the particle is moving in the positive direction. Then from 3/2 to 7/2, it's moving in the negative direction. And then from 7/2 onward, it's moving in the positive direction. So its direction is changing at 3/2 and 7/2. Between 3/2 and 7/2, there's no change in direction. So you can just integrate the velocity function, put the limits from 3/2 to 7/2, and that should give you the result directly. Okay, what's the velocity function? Velocity function is 4t squared minus 20t plus 21. Just integrate it, and that will give you the velocity function that looks like this: 4t cubed divided by 3 minus 20t squared over 2 plus 21. And now input the limits from 3/2, you can say 1.5, to 7/2, that's 3.5. And that will give you displacement from 3/2 to 7/2. That will be the same as the distance traveled in this part, right? Because there's no change in direction. If the direction is not changing, displacement and distance are the same. Okay, so what do we get from this? 20 and 2, they get cancelled, and we get 10 here. So now input 3.5, 4 into 3.5 cubed divided by 3, subtract from that 10 into 3.5 squared plus 21. Subtract from this the case when you input t equal to 1.5, and that gives you 4 into 1.5 cube over 3 minus 10 into 1.5 squared plus 21. And that should give you the result. You can see what this turns out to be. 4 into 3.5 raised to power 3 divided by 3 minus 10 into 3.5 squared plus 21. The first bracket is giving me minus 133 over 3. Subtract from this the case when you input t equal to 1.5. And that gives me 3. And that should give you the result. You can see what this turns out to be: minus 133 over 3 minus 3. Can somebody check this calculation as well? Minus 142/3, that's what I'm getting. Let's check this again. 40 squared minus 23 plus 21. That's the velocity function. 40/3 minus 20 squared root. Okay, I'm sorry. I missed a t here. This should have been in t with this as well. When we integrate 21, it should have been 21t. So we actually end up getting another number here. This is actually 21 into 3.5. And then this is also 21 into 1.5. You have to do that calculation again. With 1.5, this gives me 27/2. And then with 3.5, it's giving me 49/6. 49/6 minus 27/2. Let's find this difference. That's minus 16/3. This is the displacement from 3/2 to 7/2. It's negative. Why? Because the particle was moving in the negative direction, and that's okay. We were looking for distance traveled. When we write distance traveled, we have to make it positive because distance cannot be negative. Distance traveled in this part of the journey is 16/3, or you can say that's 5.33333. That's the distance traveled from time equals 3/2 to time equals 7/2 while the velocity was negative. Make sense? Any problems with this? No problems. Let's have a look at the next one now. Next, we've got question number 6. It says a car of mass 1600 kilograms is pulling a caravan of mass 800 kilograms. The car and the caravan are connected by a light rigid tow bar. Okay, so we've got a rigid tow bar. 1600 kg is the mass of the caravan. Sorry, mass of the car. And 800 kg is the mass of the caravan. Okay. Now they're connected by a light rigid tow bar. Rigid tow bar means that tension can sometimes be negative. Keep that in mind, okay? Because when it's a rigid object, it can push objects as well. Okay, so because string generally just pulls objects, rigid objects can also push objects. Okay, I think we talked about this earlier in the class as well. Just a reminder of that. If you end up getting a negative tension somewhere, just don't worry about that. Leave it as it is, and that will be acceptable. Okay. Everything else works the same way as it used to before. It says the resistances to the motion of the car and the caravan are 400 Newton and 250 Newton, respectively. We've got their resistances. We've got the masses given and the resistances given. They are traveling along a straight horizontal road. Given that the car and the caravan have a constant speed of 25 meters per second, find the power of the car's engine. Okay, now what's the formula that connects power and velocity? It's power equals driving force into velocity, right? Now we know the value for velocity, but what about the driving force? How do you find the driving force? Let's think about it. The speed is constant. Okay, so if the speed is constant, what does that mean? Acceleration is going to be 0, right? Constant speed means acceleration is 0. So if we were to use resultant force equals mass into acceleration on this, what do we get from that? So Let me just represent this diagram here on the side. Okay, so we have a car that has a mass of 1600 kg. Let's say this is the car. And this is the caravan. Let's represent it by V, because we can't use C for this again. Car is pulling this caravan at a speed of 25 meters per second. What are the forces acting? Car has a driving force, right? Because it's pulling that caravan. What other forces are acting along the surface? Along the surface, we would have resistance on the car. What's that? That's given to be 400 Newton. The resistance on the van is 250 Newton. What else? We've got tensions. On the car, the tension acts backwards. On the caravan, the tension acts forward. This is what we are given. Can we find the driving force somehow? Since the whole system is moving at constant velocity, you can either treat it as a whole system or do them individually. That's your choice. Let's do them individually. We've got the caravan and we've got the car. They're both moving to the right. So we can say the right side is positive. For the car, what's the forward force, driving force? What's the backward force? T and 400. That equals mass into acceleration. Acceleration is 0, so that's why on the right side we've got 0. For the caravan, the forward force is T, the backward force is 250. And this is also moving at constant speed, so acceleration is 0. So this is also equal to 0. Now from this we get tension equal to 250. Put that in the other equation. And that gives you driving force minus 250 minus 400 equals 0. And the driving force turns out to be 650 Newton. Now, once you know the driving force, you can put that here. You can say power equals 650 into velocity, which is 25. And that should give you the power of the car's engine. Let's see what this turns out to be. 650 into 25, that's 16,250 watts. That's what we were looking for in the first part. Okay. You could treat this as a whole system as well, as a single system as well. In that case, you would say, if this is the whole system, the forward force is driving force. The backward forces are 400. The forces external to the system. They are 400 and 250, and that should equal 0. And you could say driving force equals 650 Newton from that. Sometimes using the system as a whole makes things slightly quicker. In this case, you could do that. So generally, when you don't have to find tension, using the whole system is quicker. Okay, so you could use the whole system in this case like this. Make sense? Give you the same result at the end. That's what we get. Now it says the engine's power is now suddenly increased to 39 kilowatt. What does that mean? Kilowatt, that's 39,000 watts. Find the instantaneous acceleration of the car and the caravan and find the tension in the tow bar. Okay, so now power is increased instantaneously, suddenly. Okay. It was earlier moving at a constant velocity of 25 meters per second. When the power is suddenly increased, speed is not going to suddenly change to another value, right? It takes time to change for the speed to change. It will take a few seconds or a few milliseconds at least to increase. It will gradually increase. So at this instant, when the power is suddenly increased, the speed is still 25 at that point, right? It will take some fraction of a second to increase after that, right? To start increasing after that. So at this point, velocity is still 25. Speed is still 25. Can we find driving velocity, driving force from that? We know power equals driving force into velocity. The value of power is 39,000. 39,000 equals driving force into 25, and that will give you a value for driving force. Let's see what this turns out to be. Driving force is 39,000 divided by 25, that's 1,560. This is the driving force that we get, 1,560 Newton. And now what are we looking for? We're looking for acceleration and the tension. What's the connection between resultant force and acceleration? Between forces and acceleration, it's Newton's second law of motion. That's resultant force equals mass into acceleration. Again, let's use that on both the objects separately. In this case, you have to use separately because we're looking for tension as well. We've got the same two equations as before. T minus 250, that equals mass of the object. Now the speed is no longer constant, so we can't say acceleration is 0. T minus 250. So first of all, on the left side, we've got the caravan. On the right side, we've got the car. T minus 250, the mass of the caravan is 800. So that equals 800 times acceleration. That's the first equation that we've got. And the second equation would be for the car. Car is moving in the right direction as well. Forward force is driving force. So we say driving force minus 400 minus T, or T minus 400, it's the same thing. That equals mass, which is 1,600 into acceleration. Now we know the value of driving force. We have found that here. We can put that in that equation and we get 1,560 minus 400 minus T equals 1,600 times A. And now we've got two equations in which acceleration and tension are the two unknowns. We can find their values and see what they turn out to be. From the second equation, we get T equals 1,560 minus 400, that will be 1,160. This comes to the left side and that gives us minus 1,600 times A. What about tension? Tension equals 250. From the other equation, it becomes 250 plus 800 times acceleration. Now let's solve them simultaneously and see what that gives us. 250 plus 800A, that equals 1,160 minus 1,600 times A, 2,400 times acceleration. That equals 1,160 minus 250, and that's giving me 910. And the value of acceleration turns out to be 910 over 2,400, and that's 91 over 240, which is giving me 0.3792. That's the acceleration that we get. Okay, we found the acceleration. Once you've got the acceleration, you can put this back in the tension equation to get the corresponding value for tension. Tension equals 250 plus 800 into 0.3792, and that should give us the result. That's 553.33 Newton. That's the value of tension that we were looking for. Okay, so we have both the tension and acceleration from this. Make sense? Okay, so we've got the value of tension and the value of acceleration. Now let's look at the next part. It says the car and the caravan now travel up a straight hill, inclined at an angle of sine inverse of 0.05 to the horizontal at a constant speed of V meters per second. The car's engine is working at 32.5 kilowatts. And now we need to find the value of V. Remember, the V is the speed is constant. If speed is constant, that means acceleration is 0. Keep that in mind. What other information are we given? We're given the angle and we're given the power. 32,500 watts. That's the power. And what we need to find is V. What's the power formula? Power equals driving force into velocity. That's one power formula that's used mostly. We can say 32,500 equals driving force into velocity, or driving force into speed, in fact. If we can find driving force somehow, we can find the corresponding speed for that. Now, what information are we given? It's an inclined surface. It's a hill that's straight hill, looks something like this. The angle is sine inverse of 0.05. Let me write that here. Theta equals sine inverse of 0.05. If we say the angle of inclination of the plane is theta, theta equals sine inverse of 0.05. Now, what that means is we can say sine theta, that equals 0.05. So if we had to use sine theta somewhere, we could directly input this value there. We don't necessarily have to find the value of theta and then find sine theta again. We know that sine theta equals 0.05. Generally, that's why they sometimes give you angle like this, because you have to use sine theta, and in place of that, you can just input 0.05 then. Okay? All right. So this is what the inclined surface looks like. Now they're traveling up this hill. Let's say the car is here now, and the caravan is here. They're going up the hill. So car is ahead of the caravan. They're connected. Again, what are the forces acting? There's driving force of the car that's acting in this direction. There will be, so again, we have reaction here as well, but we're not considering that because that's not really affecting motion in any way, because reaction is acting perpendicular to the surface and there's no friction involved here that we have to worry about. So we're just ignoring reaction, right? It's acting here, but for our purposes, it's not making any difference. Okay. All right. So this is driving force. Then we have tension. On car, it's going to act in this direction. Caravan, it's going to act in this direction. What else? We've got weight of the car and the caravan. Now, since it's an inclined surface, weight is going to have an impact, because weight is one component of weight is going to act against motion. So we also have to consider that. Weight of car, what's that? 16,000 Newton. That's the weight of the car. And we've got the weight of the caravan. That is 8,000 Newton, because its mass was 800 kilograms, right? Yeah. What about their components? One component is going to act here, perpendicular to surface, if this angle is theta. Right? If this angle is theta, this is also theta. And the other components are going to act along the surface in this direction and in this direction. For the caravan, this would be 8,000 into sine of theta. And for the car, it would be 16,000 into sine of theta. These are the weight components acting along the surface like this. What else? We've got resistances, remember? We were given that the resistances to the motion of the car and the caravan, they are 400 and 250 respectively. They're still acting. On the caravan, this resistance is 250 Newton. And in the car, it was 400 Newton. These are all the forces that are acting now. What are we looking for? We're looking for driving force somehow. Acceleration is again 0. Since we're not looking for tension, again, you could use the whole system. In that case, you would not have to worry about tension. And you could say Just subtract from the forward forces the backward forces and put them equal to 0. Okay. Or you can do them separately. That's also fine. If you're used to doing that, you've got the caravan, you've got the car. Let's use resultant force equals mass into acceleration, both of them separately. What are the forces acting? On the car, we've got driving force, we've got the weight component, we've got tension, we've got resistance. On the caravan, we've got tension, we've got resistance, and this weight component. And that's it. Now, for the caravan, we can say it's T minus 250 minus 8,000 sine theta. That equals mass into acceleration. Whatever the mass is, acceleration is 0. Why? Because it's constant speed. We can find the value of t from this. That's t minus 250 minus 8,000 into sine theta. Remember what sine theta was? Sine theta was 0.05. We can use that value here. This equals 0. We can find the value of t from this. Let's see what this turns out to be. 250 plus 8,000 into 0.05. The tension turns out to be 650 Newton. Okay, now the other equation would be forward force for car, which is driving force, minus the backward forces, which are T 416,000 sine of theta. That equals mass into acceleration. Again, acceleration is 0, so the right side is just 0. We know the value of tension now. Tension value is 650. And then you have minus 400 minus 16,000 into sine theta, which is 0.05. That equals 0. And you can get the value of driving force from this. Let's see what this turns out to be. 650 plus 400 plus 16,000 into 0.05. And that's giving me 1850 Newton. That's the driving force. Once you've got the driving force, you can put this back in this equation to get the corresponding speed. So that's 32,500 equals 1850 into V, and that will give you the value for V. You can see what this turns out to be. 32,500 divided by 1850, and that's giving me 17.568. You can say that's 17.6 meters per second. That's the speed that we were looking for. That's quite some work for 3 marks, but this is how you could do it. You could reduce some of this working by considering it as a single system. Let me write down an equation for that as well. If you were to consider it as a whole system, you would get this equation. Driving force minus 400 minus 16,000 sine theta. These are the backward forces, right? Minus 8,000 sine theta minus 250. That equals 0. And that would have given you driving force directly. And that was 1850. And then you could just input that back in that power formula to get the corresponding speed for that. This could be another way of thinking about this. You could also do it this way, as a whole system. Make sense? Any problems with this? No issues? Okay, let's look at the last question now. The next question, that's question number 7. And then we end. So now we have another inclined plane. There are 2 inclined planes, one on the left side, one on the right side. There are 2 particles, A and B. Their masses are given. Light and extensible string with small pulley. The string is short into 2 parts and the string is divided. So it's just a description of that diagram. There's nothing new that's written here. It says it's given that plane P is smooth, plane Q is rough, and the particles are in limiting equilibrium. What does that remind you of? Whenever something is in limiting equilibrium, that means F equals mu R. Friction equals its maximum value. That means F equals mu R. We need to find the coefficient of friction between particle B and plane Q. So we need to find the value of mu somehow. It's equilibrium. We just equate opposite forces. Let's represent all the forces and then equate them. What are the forces acting on the particle A, first of all? We've got reaction. Now, in this case, P is smooth. So the left part is smooth. We would not really need reaction here because there's no friction, but you can just represent it if you want. This is reaction in this case. Let's call this reaction for A. There's weight of object A, which is 20 Newton. There is tension acting in this direction. And that's it. These are all the forces acting on particle A. The components of weight here are going to be this. This angle is 10 degrees. So this component will be 20 cos 10. And the other will be acting down the plane, which is 20 sin 10. These are all the forces acting on the object A. Similarly, let's write down the forces acting on the object B. What are those forces? There's reaction in this direction. There is weight acting vertically downwards, which would have a magnitude of 30 Newton. There's tension acting in this direction. And there's friction as well. Let's see in which direction is that going to act. Does that say here anywhere? Okay, the particles are in limiting equilibrium. Limiting equilibrium means B is either about to move upwards or it's about to move downwards. In which direction would it be about to move? Down the plane or up the plane? And how would you know that? B has more weight and A has less weight. But the angles are also different. You can see B is also on a steeper surface. Surface P is less steep. So both of those things basically tell you, since B has more weight and it's also on a steeper surface, B is likely to go down the plane, right? So that means B is just about to move down the plane. If B is just about to move down the plane, where is friction going to act? Friction is going to act up the plane, right? Because B will be just about to move down the plane. Make sense? How do we infer that? Using the weights and the steepness. Both of them tell you that B is likely to go down the plane. If the surfaces were smooth, B will start moving downwards. But in this case, friction stops it from moving. So friction acts in this direction. All right. Now, these are all the forces acting on the particle B. Let's resolve these forces now. We've got weight acting vertically downwards. Let's resolve weight. What are the two components of weight? One is going to act in this direction. If this angle is 20, this angle here is also 20. So this component would be 30 cos 20. And down the plane, it would be 30 sin 20. Now, since it's equilibrium, it's limiting equilibrium, we just have to equate the opposite forces. That means 20 sin theta should equal T. RA should equal 20 cos 10, although we don't need to use that. Let's leave it here. 30 cos 20 equals R, and T plus F equals 30 sin 20. Let's equate the opposite forces for A. We don't need reaction here, just ignore that. 20 sin 10 should equal T. We get the value of T from this. Let's see what this turns out to be. 20 sine of 10, that's giving me 3.473. That's the value of tension. Okay, we found the value of tension from this. Now, let's look at B, the other particle. For B, let's equate the opposite forces. R equals this. So we get R equal to 30 cos 20. Let's see what that gives us. 30 cos of 20. That's 28.19. Let's equate forces acting along the plane. That's going to be T plus F, that equals 30 sine 20. All right. Now we know the value of tension, that's 3.473 plus friction. Friction is mu into R. Mu is what we have to find out. Let's leave R as this. 30 sine 20, that's giving me 10.261 on the right side. Now let's input the value of R here as well. 3.473 plus mu into 28.19, that equals 10.261. And you can get the value of mu from this and see what that turns out to be. 10.261 minus 3.473 divided by 28.19. And that is giving me 0.2408. And that's the final answer. If leave it like this if you want, or you can round it off to 0.241. That's the value of mu that we were looking for. Okay, so we just resolve the forces, equate the opposite forces. This is the result that we get. Okay, that's 7 part A. Now let's look at the next one. It says it's given instead that both planes are smooth and that the particles are released from rest at the same horizontal level. Find the time taken until the difference in the vertical height of the particles is 1 meter. You should assume that this occurs before A reaches the pulley or B reaches the bottom of the plane. Okay, now both the surfaces are smooth and there's no friction. Let me just copy this diagram here. Okay, so this is the diagram that we're given. Both the surfaces are smooth now. That means there's no friction on any of the two surfaces. And the particles are released from rest at the same horizontal level. So they're released from rest at the same horizontal level. This level is the same. Find the time taken until the difference in the vertical height of the particles is 1 meter. Okay. Can the energy method work here? Let's think about that. Force and displacement, there's no time there, right? We can use power equals working over time. Oh, that's wrong ahead. Okay, so energy method cannot be used to find time, I think here. Let's use acceleration. They're starting from rest, and we can find the displacements using that. Okay. So we need to find the time taken until the vertical height of the particles is 1 meter. Difference between the vertical height. So basically what happens is, since the surfaces are smooth, B is going to move down the plane. Let's say it comes here. A will move the same distance up the plane. Let's say that comes here. Let's say this is A and this is B. At this point, they're saying the difference between vertical heights. This is 1 meter. How much time does it take to get to this point? So it's that the difference between vertical heights, that becomes 1 meter. Now, how can we think about this? Let's consider the journey for both particles. A is moving up the plane, Let's consider this direction positive for that. B is moving down the plane. Let's consider this direction positive for that. Okay. This is A and this is B. A is moving in this direction and B is moving in this direction. What's the initial velocity for both the particles? They are both starting from rest, right? They're both released from rest. So that means initial velocity for A is 0, initial velocity for B is 0. Both of them have the same initial velocity. What else do we know? We have to find the time taken. What we can also do is we can find the acceleration. Both the surfaces are smooth, so what we can actually do is we can find accelerations for these first of all. Then we can use kinematics after that, because we know the forces acting on the two particles. On A, we have found that the weight component acting down the plane is 20 sine 10. So this component is 20 sine 10. And this one is T. These were the two forces acting along the plane for A. And for B, we've got T and 30 sine 20. In this direction, we've got tension. And in this direction, we've got 30 sine 20. So what we can do is we can use these forces to find acceleration of these two particles while they are in motion and the string is taut. A is moving up the plane, so the forward force is going to be tension for A. Backward force is 20 sine 10. So T minus 20 sine 10, that equals mass of A, which is 2 times acceleration. And for B, we can say 30 sine 20 is the forward force, T is the backward force, and that gives us 30 sine 20 minus T equal to 3 times A. We can find the value of acceleration from this. T equals 2A plus 20 sine 10, and T equals 30 sine 20 minus 3 times A. We get 20 plus 20 sine 10 equal to 30 sine 20 minus 3 times A. I'm sorry, this goes 2A there, not 20. 2A plus 20 sine 10. That equals 30 sine 20 minus 3 times A. And that will give us 5A equals this. Let's calculate this. 3 sine 20 minus 20 sine 10. And then that divided by 5. Acceleration is turning out to be 1.3575. That's the acceleration of both the particles. A is moving up the plane. Acceleration for that is 1.3575. V is moving down the plane. Acceleration for that is also 1.3575. So we know their initial velocities and we know their acceleration. Now, what else do we know? We need to find the time taken. Okay, that's what we have to consider. But there's another piece of information that we're given, and they're saying the difference between the vertical heights of the particle is 1 meter. Let's think about this. A is moving up the plane, right? So A is moving in this direction. This is the vertical height of A. Let's call this HA. Height of A. We know that this angle is 10 degrees. What else do we know? This is the displacement by A, SA. What we can do is we can say HA here divided by SA. S is the displacement along the plane. H is vertical height. Okay. Perpendicular over hypotenuse, that equals sine of 10. Okay. Now what about B? B is moving down the plane. This is the distance that it travels down the plane. Let's call this displacement of B. The height of B that's decreasing here, that's HB. And the angle here is 20. We can say HB over SB equals sine of 20. Okay. From this, what we can do is we can say HA equals SA into sine 10. Right? And from here, we can say HB equals SB into sine of 20. Does that make sense? So we were given something about the vertical height, the change in vertical height. That was, the total of that was 1. So basically we're saying A is moving a certain distance upwards and B is moving a certain distance downwards vertically. We're calling this HA and we're calling this HB. Since the total difference in the vertical height at that point is 1 meter, what we can say is HA plus HB, that should equal 1 meter. That should equal 1. Make sense? Because the total difference between vertical heights, that was supposed to be 1. That means whatever distance A has traveled vertically upwards, that plus whatever distance B has traveled vertically downwards, their sum has to equal 1. Okay? Now from this, what we can say, SA, because we know HA equals this, we can say SA into sine of 10 plus SB into sine of 20, that should equal 1. We get some relationship between their displacements. This is how their displacements can be connected. Okay? Now, what are we looking for? We're looking for the time taken. They were released from the same time. So time is basically going to be common between them. So if we say the time taken by particle A is T, it's going to be the same for particle B. The time taken by particle B is also going to be T because they started from the same time. And the point that we're considering, until that point, the same time interval would have passed. So we can say both of them have time T. Can we connect all of these things now? Since we have a relationship between SA and SB now, and we also know U, A, and T from both the equations, which equation connects these things? S equals UT plus half AT squared. We can use that to make an equation. What would SA be? I'm using this formula, this constant acceleration formula. Let me write that on the side. S equals UT plus half AT squared. Let's use that on both the particles. Let's use that on A and on B. If we use that on A, that gives us UT, which is 0 times T, plus half into A, which is 1.3575 into T squared, multiplied by sine of 10, plus SB, which is 0T plus 1 over 2 into A, which is 1.3575 for this as well, into T squared, into sine of 20. This should equal 1. This is an equation that we get in terms of T. And now we can solve this equation, and that should give us the value of T. Let's see what we get from this. This is 0, that gets eliminated. Let's multiply these. 1.3575 divided by 2 into sine of 10 And that's giving me 0.11786 t squared plus, let's multiply these, 1.3575 divided by 2 into sine of 20. That is giving me 0.23215 t squared equals 1. Let's add them up together, plus 0.11786. This is 0.35000, so that's 0.35 t squared equals 1. And the value of t squared equals 1 divided by this, which is 2.8571. And the time taken that I'm getting from this is 1.69 seconds. This is the time when the difference between vertical heights of the particles becomes 1 meter. And that is what we were looking for here. Is that okay? That was pretty complicated, quite complicated. The key thing here was actually figuring this out. How to connect those vertical heights with their displacements. And then how to make this equation, basically. And that was the tricky part. How to make an equation that connects their displacements given the difference between their vertical heights. Okay? I hope that makes sense. Any questions? Or was that too complicated and you got confused somewhere or blank somewhere? Make sense to everyone? Okay, great. So that's it for today then. This was November 2020, paper 4, variant 3. We end our class here for today. Tomorrow, we are only going to have a P3 session for those who are enrolled in that. And then the next mechanics class will be on Monday, inshallah. I'll be telling you which papers to attempt for that. Please make sure to attempt those questions before next class. At least the questions that look difficult to you, at least attempt them. And then let me know the questions that you want me to discuss. But that's it for today. If you have no questions, we will end this class here and I will see you again in the next one. Allah Hafiz. Yes, Rizal? For preparation or in the exam? Well, it's the same for all papers, generally. What you do is you start questions in order generally because you will see that the first few questions mostly are going to be easier and then they will gradually start increasing difficulty level. It's not always going to be like that. You will get some parts in the middle that are quite complicated. And the rule is whenever you get stuck at a question, you just make sure not to stop there and spend too much time on that question. So if it's a 2 or 3 mark question, if you spend 2-3 minutes on that and you can't figure out what to do, you move on and you come back to that at the end of the paper. If you have figured out some direction, then don't stop in the middle, then complete that and then move on. But if you get stuck and you can't figure out something and it's a 2-3 mark question and you've spent the same amount of minutes, same number of minutes on that almost, skip that, come back to that later. That's the general rule that you need to remember. What happens is mostly the questions on kinematics, they take longer. So you can perhaps leave them for the end. Not the ones that involve equations, but the ones that have these constant acceleration formulas, like the one that we did at the end, this last one. And you have to use Newton's second law of motion and kinematics concepts together, these are the questions that are generally longer. So they take more time. You can leave them for the end, but it's basically a trade-off that if you leave them for the end and if you left for too little time at the end, too little time for them at the end, then you would kind of be thinking that, okay, there are only 10 minutes left and there's so much to do and you might not get ideas for this. So if you do leave it for the end, leave enough time for this as well. So do the other questions. So forces and equilibrium questions, they generally don't take that long. Newton's second law of motion, the Newton's second law of motion part, that's quicker. If it's coming along with kinematics, then it might take longer. Then kinematics, if you have a graph question, generally they're easy. If they have a graph given already in the question, they're easier to do. You can do that earlier as well. If it's an equation question where you have a velocity equation or an acceleration equation or a displacement equation, they generally are not that time taking as well. You can do them in the middle as well. Momentum question, if it comes with energy, that's relatively easier. If it comes with kinematics, that also takes time. Work, energy, power, and kinematics. These are two topics that take relatively more time. Kinematics more than work, energy, power. So what you can do is you can do the shorter questions earlier and save time on them so that we have more time at the end for the relatively bigger questions. And while you do all of that, just remember not to get stuck anywhere. That's the most important thing that we need to remember for all the papers. That you don't get stuck at any question in the middle of the exam, because what happens then is that you end up missing out on some easier questions in other parts of the paper, and that is what is going to make you lose grades. But if you don't get stuck and are at least able to do all the relatively average questions, and then you spend time on the difficult questions at the end, hopefully you will do well at that, because you'll be saving some time and in the earlier parts of the paper, leaving more time for the end, and then you'll have confidence as well that you've done most of the paper, and you'll have more chance of cracking the more difficult questions in the paper as well. There's no specific order that I generally recommend that everyone should follow. It works different for every single person. You might find one topic easier than another topic. Another person might find another topic easier. So do the questions that you find easier first, and then move on to the others that are more difficult. But while you do that, leave enough time for those remaining questions as well by doing those easier questions in a relatively shorter time. Okay, so I'll see you again in the next session, inshallah, on mechanics. That will be on Monday. All right. Okay, Allah Hafiz.